Hey, good morning, Physical Geology. This is Robert Lopez, your instructor for this course. And today I'm going to kind of go through the Metamorphic Rocks lab, do some of the experiments, have you observe what's happening, and then you can write down what you observe in the lab here that I have in front of you. You can sort of read through this. I know I've talked about this in my video lecture, so you'll kind of get an idea about regional metamorphism and contact metamorphism. And remember, the third one is that hydrothermal metamorphism or metasomatism. But as you read through the lab here, we'll come back to this figure here because this figure is kind of nice. I like it in the terms that it describes this progressive or prograde metamorphism as you're going from the protolith, in this case the shale. If I can get it to high enough grade, remember grade refers to temperature. If I can get it to high enough grade, so low grade, this temperature is between about 150 and about 300 or so. I turn it into slate, or slate or phyllite would be the next category that goes here. So there's no phyllite on this figure, but phyllite would be the next metamorphic rock, still under the low grade, but maybe a little bit more pressure. The rock looks a little bit different than slate, a little bit more shiny, of a sheen. But then if I get it a little bit higher grade and pressure, I get the schist. And then you can see I can prograde all the way to gneiss. So essentially I can take a shale, and if I get it hot enough in terms of grade and enough pressure, I can convert it into a metamorphic gneiss. So this is what I call the normal temperature, normal pressure, or normal grade, normal pressure regime or path. And you can see that another path is where you stay relatively low pressure, less than 10 kilometers burial. And so you're pretty shallow levels, but you get lots of heat. The only way this happens is if you get magma intruding into the crust and it's burning the adjacent country rock, right? And so that's what we call contact metamorphism. And the Hornfels facies there will result in this pretty dramatic roof pendant. So I talk about these roof pendants, and these are basically the contact metamorphic rocks, or the Hornfels facies, where in this case, this is Sierra Nevada granitic rock, intruded during the Mesozoic time. So these are magma chambers, temperatures anywhere from 800 to 900 degrees centigrade, and they're burning contact metamorphic the adjacent country rocks here. So that becomes the roof pendants there, right? So that's a Hornfels facies. So that's a second path. And then finally, the third path is where you stay relatively low grade, low temperatures, but you go to pretty high pressures. And so we call that blue schist facies. And blue schist facies occurs only in subduction zones. You can see there's another region that's not quite shown here, but it's called eclogite. And eclogite is related to blue schist, but it has a little bit more temperature. But really, blue schist is a lower grade, high pressure metamorphic rock. So as we go through the lab here, the first experiment is going to make you observe rates of metamorphism and how fluids and temperatures can enhance metamorphic processes. So what we're going to do with this first experiment, we're going to take some aspirin. So we'll take a couple of aspirin. We'll take some baking soda, right? And then we're going to mix these into what I have here. I have a little test tube here, and we'll put it in a test tube and we'll see what the reaction is. So let me put these together, and obviously I'll need to grind I have a mortar and pestle here. So I'll take my couple aspirin here, and then I'll grind these guys up, and then we'll make a powder. So let me do that, and then I'll put things together. Here I've ground up the aspirin and the baking soda. So now I'm going to put in the test tube here and see what happens. So I've made little boats out of paper here so I can get the material in there. So there's the aspirin in the test tube. Now we'll put the baking powder in here and see what happens. So remember, we're under dry conditions here with no fluids in it yet. And so if you kind of mix this around, you can put your thumb on top here, kind of shake it around, and we'll see that, did you observe a chemical reaction? So you can either check mark here or check mark over here. Now we're going to add some water, about a quarter to half tablespoon. And I'll add some water in here using this straw. We'll see what happens when I add the water. So what I see some bubbling. I don't know if you can make out that bubbling. So you can answer the questions and describe what you see here at letter B. Now the second part of this experiment is going to have us look at cold and hot water and how it's going to affect these white crystals. So I just have some generic white crystals, which are essentially sugar crystals, and we're going to see what happens under cold and hot water. And what you'll see for this lab, I'm going to have, I guess we'll do the experiment at least 3 times. So I have 3 little beakers here, and in each beaker they asked me to use about 150 mils. I only have 100 mil beakers, and I'm just going to fill it up to about, well, close, a little bit over, maybe 90, because I don't have large enough beakers, but we'll get it up there. So I'm going to pour some cold, all right, so here I've set up a thermometer with the cold water. You can see the temperature's dropping around 6.7. It's kind of stabilizing there, so this is 6.6. So let's go with 6.6. We'll stop this here. And so that'll be our first cold water experiment. And then it says in the lab that we need to put a level teaspoon of white crystals in there, so I'll do that now. And then we need to get our timer ready, so I have my phone here. We'll get this going. So as soon as we pour the crystals in, we'll put it in there and then we'll start. And we'll see how quickly this dissolves. And I see a lot of crystals on the bottom. You can sort of make them out there. Let's zoom in a little bit. You can see the crystals down there. The sugar is not really dissolving, so let's keep mixing it. And I'm starting to see some, I still see crystals at the bottom. You can sort of make them out. They're not totally dissolved. We'll keep mixing. The timer's still going. And there's a few crystals there, so well, they're pretty much dissolved now. We'll stop here. So for our first temperature was 6.6 degrees centigrade, and it took a little over a minute, 1 minute 3 seconds. So you'd want to record that for your first data point, right? So we'll put this guy aside, and we'll take a second one, and we'll do the same thing with cold water. So again, we'll take our temperature reading here, and so again we'll hit the start button here, and so we're at 8. So it looks like our second temperature reading is around 7.6. So we'll stop that. And then we'll do the same experiment with a spoonful of sugar here. And we'll see what happens. We'll start the timer. There's still a lot of sugar down there. Still pretty cloudy. See the sugar crystals still. Well, this one's pretty much dissolved now, so we'll stop it there. So that one took about 58 seconds. So the first one took 1 minute and 3 seconds, so 63 seconds for the first one, 58 for the second one. We'll put that aside, and then we'll do our third one here. Well, it looks like our third one is leveling out here at 8.7 degrees centigrade. All right, so record that for your third cold water try. And again, we'll put the sugar crystals in here and see how long it's going to take. We'll start our timer. This one looks like it's pretty much dissolved there. So that took about 50 seconds. All right, so that'll be for our cold water experiment. Now I'll set up the hot water experiment. Okay, so now I'm back with the hot water, and you can see I have it, we'll pick this one at about maybe, it's cooling off, so the temperature's sort of dropping, and we'll equilibrate it there around 81 degrees. Let's do that for the first try. And now we'll get our timer ready, and then we'll get our spoonful of sugar here. And we'll start the timer. We'll see how quickly this goes. And you can see that it's already dissolved. So literally it took about 8 seconds for that first one. Let's do another one here. And again, we'll take our temperature. It's probably going to be a little bit cooler because it's been sitting here for a little bit. So about 78.1. 78.1 for the second try. And on this one, we'll do the same trick here. Get our sugar crystals ready. Put in here and start. And it's pretty much dissolved. So about 10 seconds for that one. And finally for our third try, this might be a little bit cooler on this one. Let's equilibrate. Looks like 76.9. 76.9 for the third temperature. We'll get our sugar crystals going. Put them in here, do the start. And they're pretty much dissolved there. So about 7 seconds. So there we go. There's our experiment. So now your job is to complete this data table on page 94. Remember, we're using about 90 milliliters. But you want to record the times here and the different temperatures we had here. Then you can answer these questions here. And then you can do the calculations for the rate of cooling in terms of the hot water being faster. And then you can answer the questions in terms of rate of processes for metamorphic rocks. Now the next part of the lab deals with phase diagrams, and these are really important in metamorphic rocks in terms of index minerals. And an index mineral is one that forms at particular temperatures and pressures, and they're really like a window or clue to the conditions the metamorphic rock experienced. In fact, if you talk to metamorphic petrologists, they say that the metamorphic rock enjoyed those conditions. But at any rate, you'll see I talk about these stability fields and different phases, and a really important group of minerals are kyanite, andalusite, and sillimanite. All three of these are said to be polymorphs, right? Remember polymorphs? They have the same chemical composition, AO2SiO5, but they have different mineral or lattice structures, right? Crystalline structures, because they're forming at different pressures and temperatures, right? So on the next diagram, we find the stability fields for kyanite, andalusite, and sillimanite. And so there's some questions about kilobars. So remember, the kilobars are on the left side here. So the depth is on the right. So when you're looking at kilobars, make sure you use the left side of the diagram here and the temperature. So these are pretty straightforward questions. Remember that Le Chatelier's principle states that a system will react to an external input in a way to lessen that input. So in other words, if I add more pressure to the system is going to react in a way to lessen that pressure, the effect of that pressure. So it'll probably compact to a denser form, so to reduce that extra pressure. So anyways, you kind of keep going through these questions, and then you'll see that there's a question here about more than one rock can become gneiss. In my video lectures, I do talk about that prograde metamorphism. So remember, in the beginning here, we talked about how shale can go all the way to gneiss, but another rock that can be metamorphosed to gneiss is an igneous plutonic rock, like a granite, some sort of granitic rock, right? And why do they reach the same metamorphic rock? Is because they reach the same grade of metamorphism, that same pressure and temperature, right? And then here's a little bit about metamorphic facies. So read about this. Your book has a good explanation of this as well. I talk about it in my video lectures. It really deals with this next figure on page 96, where you're looking at these metamorphic windows. You know, think of this blue schist facies as subduction zones. It's only where you're seeing high pressure but low temperature. You know, the roof pendants are up here for the hornfels. And so kind of read through this, and as you're reading the questions and answering these questions, you can kind of pigeonhole where your sample is going to be and what conditions are going to occur at these different scenarios here.